Now the Doppler effect leads to frequency dispersion or time selective fading. So given a maximum frequency Doppler shift f sub m, if the symbol time is greater than the inverse of this value, which is a time value, we get time selective fading. Meaning what? Let's say that we have this symbol, right? And this is t sub s. Now if t sub s is greater than 1 over fm, meaning that it is likely that a time fade will hit this symbol. The power will drop below the minimum received power required for modulation, or what we called receiver sensitivity, meaning that we have now a time selective fading. In contrast, if the symbol duration is less than 1 over fm, this event is highly unlikely. Okay, so again, this is a random event, so we need to deal with it statistically. So we compute the autocorrelation function, which has this general form. J sub 0 is the Bessel function of the first kind and 0 order. Okay, this is called the Doppler spectrum, and if the Doppler spectrum, if you can see, it's a bit complicated. If we assume it has some nice shape, it's called a classical or Jake's spectrum or bathtub spectrum. Bathtub spectrum because it looks like a bathtub, like this. If you draw equation 58, you'll get this nice bathtub shape, and those are fm and minus fm. Those are those values that the spectrum goes to infinity here. Now we are interested in the average number of times the power drops below the receiver sensitivity, which is called the level crossing rate. For the Jake's spectrum, it has this nice form in equation 59. Fm is given, Prx is the average value, and R squared is usually the P minimum or the receiver sensitivity. We are interested in another quantity, which is called the average duration of fade. So let's say we have a level crossing happening. Now, how long would the received power be less than the receiver sensitivity, meaning that how long would the outage persist? Of course, it's a random quantity, so we are interested in the average duration of this fade or outage, right? Generally speaking, ADF is P outage over the level crossing rate. For the Jake's spectrum or bathtub model, we have this form in equation 61, which is a bit simple. Now rho, again, it's actually, if you think about it, it's a kind of SNR, but again R squared is the P minimum, so it's P minimum over P average. Okay, let's take an example. Now we have system operating at 900 megahertz. The receiver sensitivity P minimum in linear scale is 1 milliwatt. The average received power is 10 dBs above the receiver sensitivity. If the channel suffers from Rayleigh fading and Doppler spectrum having Jake's spectrum or Jake's form with maximum Doppler shift of 50 Hz, we need to find the outage probability, P out, the level crossing rate, LCR, and the average duration of fade. The last one is a bit interesting. If we want to have ADF of 2 milliseconds, what should be the minimum Doppler shift? Let's compute first the Prx, which is the P minimum in dBm plus 10 dBs. So we get 11 dBs. Now we need to convert it back to linear scale because to compute the P outage, the LCR or ADF, we need to have linear scaled power. So the outage probability is very simple. We call that sigma square is actually the received power, and R is the square root of P minimum, so R square is the P minimum. You just plug them in here in linear scale, you get 4% outage probability. Now you compute the LCR. Again, you just put in the values here. This is 50. This is the p-minimum that we computed, and this is the PRX. Again, you plug them in and you get 24 level crossing per second. The ADF follows directly. You just divide P out by LCR. You get 1.63 millisecond is the average duration in which in a level crossing event you stay underneath the receiver sensitivity. The final demand here, or part of the question, is we need to find the minimum Doppler shift, which is the FM, right, to get an ADF greater than 2 milliseconds. Again, you plug in the ADF expression, rho is given, right? You need to find FM, which is unknown. Here, when you solve it, you need to have a maximum Doppler shift less than 80 Hz.